Okay, so in the last few weeks, we talked about the minimum quantum mechanics. So starting from the wave-particle duality, and we explained to you why do we want to use the sorting equation to describe the particles in the subatomic world. And then we solved one important example. This one-dimensional infinite square wave potential to show you the structure of the solution of the sorting equation. And that structure is very universal. So even if we move on from the infinite square root potential to more realistic potentials, like harmonic potentials, like parabola, or like Coulomb potentials, 1 over r, like in the case of atomic physics, the interaction between electrons and the nucleus is through this Coulomb interaction. The force is inverse proportional to r squared, and potential is inverse proportional to r, so 1 over r potential. And then moving forward to nuclear forces, and interaction can be approximated by roughly a square potential, but in 3D. So in all of those realistic potentials, and in the future, you may encounter even more complicated interaction potentials. But the solutions are very similar to the square wave potential, meaning that the energies are quantized. So in many of these cases, if you want to measure the energy particles, and you don't get, multiple values are allowed, but they're not continuous. And each of the energy value corresponding to the eigenstate, the eigenwave function. Okay. And each of these eigenstates satisfy this autonormality condition and put all the different waveforms together by linearly combining them, and we're not missing any function. So that guarantees that our solution is complete. Okay. So many of the things can be seen already from the infinite square wave potential. Then moving forward, in the next semester, in 447, we're going to come back to the quantum mechanics and getting into the details of solving those potentials. And those require us to introduce some of the new mathematical skills. And also the solutions are going to be useful for to better understand quantum mechanics. But we don't want until we finish learning quantum mechanics to get back to nuclear physics. Nuclear physics and interaction relations matter is really our goal, and want to give you better motivations before we learn more about quantum mechanics. So that is why we are moving on to the second part of this course. It's mainly nuclear physics. And we use one example, the model example, just like in the first part, we have the infinite square wave potential. So the one most important example in the second part will be this nuclear model in using deuteron, so neutron-proton systems. It's a way to show you how to describe nuclear physics. And along the line, we'll mention a few things about atomic physics, but that will not be our main focus. In fact, the next semester, when we solve the three-dimensional sorting equation much more rigorously, we are going to use this 1 over potential as example. Then you will see more about this new atomic physics. Okay, so that's that. Then let's get started. So first, in nuclear physics, if you step back a little bit, if you want to understand how interaction, how radiation interact with matter, then in this class we mainly cover about the 3 different kind of 3 radiations, right? Neutron interaction, charged particle interaction, and photon interaction. And among the 3 of them, neutron interaction is the most important one because the behavior is so different from everything I learned before. Neutrons have no charge, and so they don't interact with atoms, mainly nucleus, through Coulomb interactions. Its interaction itself is a nuclear force. Okay, so and the behavior of a neutron is not a simple particles anymore. So we have to treat the neutrons as both a particle and a wave. and energy can be quantized if you put neutrons in certain potential field, like when you put the neutron next to a proton. So we're going to use a deuteron, the structure of deuteron, as an example to learn about nuclear physics. And then the more complicated structures of nuclides are similar, but conceptually, so the mathematically more challenging, but conceptually similar to the deuteron. So before getting there, let's first talk about a few of the common nuclear properties and the terminology of nuclides. Okay. So that'd be the topic for today. So first, the terminology. So this is important in arguably every field because we need to be on the same page. Okay. So the terminology of nuclides. So nuclear physics, we use this symbol right here. So X, and A, Z, N to describe a nuclide. So here, X is the chemical symbol. So for instance, we talk about the hydrogen, then this X will be H. And if we talk about the uranium, then X will be U. Okay. So this X is redundant with this Z. What is the Z? Z is so-called the atomic number. So Z here is the atomic number. Okay, so Z is the atomic number. Let me write it here. So Z is the atomic number. And it's basically the number of protons inside the nucleus. Okay. So since the entire atom is neutral, then the number of protons is the same as the number of electrons. So the charge, so in other words, number of protons also means it is the charge of the nucleus. Charge of the nucleus. If you know the Z and its number of protons, then the charge of nucleus will be positive Z times E. Okay. And that's just, as I just briefly mentioned, so number of protons is also the same as the number of electrons. Right. So we know the model or atoms inside the center. We have the nucleus. Nucleus is made of neutrons, some number of neutrons, and some number of protons. Neutrons have no charge, so proton carry the same charge of electron. So we'll have some number of protons, then to maintain the overall neutral state, then we should have the same number of electrons. Okay. So, and as we know, the chemical property, the so-called chemical properties of atom, is mainly determined by the electrons. So chemistry is all about how the electrons bond with each other and form chemical bonds. So, and that is why this Z, although it's a number of protons, it's also the number of electrons. It has the same information of this chemical symbol. So you can roughly say, let me write this down first. So the Z, atomic number Z, and the chemical symbol X are redundant. So that is why oftentimes we don't write this Z. So when we put down the chemical symbol, let's say carbon, then we don't have to specify the atomic number 6, okay? Because they are redundant. If you want to know how many number of protons or how many number of electrons inside the atom, you can find it out from the periodic table. Okay. So let me add one more comment on this. So I'm quoting exactly what Schrodinger said. So it's not what I cite. So Schrodinger said that after he established his Schrodinger equation, he said, in principle, almost everything about physics and everything about chemistry is known. So of course, this is not to belittle the work of the chemist, but on the other hand, in principle, if we know the interaction, in this case, with interaction will be Coulombic between the electron and the proton, then we should be able to solve the Schrodinger equation and find out the behavior of all the electrons. And if we know the behavior of the electrons, then we know the chemical properties of the atom. Okay, of course, this in principle, although it's done, but in reality, it still takes a lot of effort to solve the Schrodinger equation, especially in the case of when we have more than one electrons. So only hydrogen has one electron. So when we have more than one electrons, then we have to solve the Schrodinger equation for every, well, not for all the electrons. Okay. So all the electrons described by one wave function, and see the dimensionality of that differential equation become very, very high. So it's not that easy to solve. So in fact, in the work in the last 100 years on computer chemistry, it spanned how to solve this many-body Schrodinger equation. Okay. But in principle, it is deterministic. If we know the interaction, then the behavior, the wave functions are governed by this Schrodinger equation, although computation can be very expensive. Okay, so this is the Z, the atomic number, and X is the chemical symbol. Then what is A? So this A, right here. So A is called the mass number. Okay, so and N is the number of neutrons. Okay, so we know inside the nucleus are neutron protons. So Z is the number. Z is the number of protons. N is the number of neutrons. So this mass number A will be equal to Z plus N. Okay. So number of neutrons plus number of protons plus the number of neutrons. Okay. So this mass number is really the total number of nucleons. Number of nucleons. So by nucleon, we mean either neutron or proton. Okay. So once we know A, by adding the number of neutron protons together, we can also know the mass, the total mass. So total mass of the nucleus and also total mass of the atom. The fact is that the mass of proton is almost the same with the mass of the neutron. Okay. So, but for electrons are much lighter. So the mass of neutron mass proton is roughly 2,000 times of the mass of electron. So that is why when we add up the mass together, we want to know the total mass of the atom. It is roughly the same as the total mass of the nucleus. Electrons are so light that when we consider the mass of the atom, they are negligible. Okay, that's why the mass of an atom is essentially the same as the mass of the nucleus. If you think about that, that is a quite amazing fact. So we know the size, okay, the size will come back to that later. The size of nucleus is very, very small compared to the size of the atom. And all the mass, almost all the mass are concentrated to this one tiny spot at the nucleus. Okay, and this number, we call that the united, 1 second. Yeah, I think let me just write it down here. Okay, so this mass of the proton, and it's approximated by the same as the mass of electron. We call this as U. It's the unified atomic weight. Okay, to treat the number of electrons, the mass of the protons and the mass of the neutrons to be same of U. Okay, and inside the nucleus, oftentimes we have slightly more neutrons than the protons. Okay, so this N is slightly more than Z, okay, and approximately the same. And for many items, they are indeed the same. So N is either equal to Z or slightly more than Z. So then this mass number A will be slightly larger than twice Z. Okay. So that is the mass number. Okay. And because of redundancy between the X and Z, so we don't write down the Z. If you write down the X, we have the chemical symbol. Then we can look up the periodic table, find out the atomic number. But number of neutrons can be different. So for the same element, I say hydrogen, then we can have no neutrons, then just one proton. Then N would be 0. Okay, then A is equal to 1. Then we can have maybe 1 neutrons there, 1 neutron. So 1 neutron, one proton system that we deuteron, then A will equal to 2. So if we know the X and we know the number of neutrons N here, then we can have the A. So there's some redundancy there as well. So oftentimes we don't write down the number of neutrons. We only write down the mass number A. So oftentimes what we only need is this X, this chemical symbol, and then the mass number. So with this tool, with this X, as I mentioned, you can look up the periodic table and find out the atomic number and how many number of protons are inside the nucleus. Then with this total mass number A, okay, with total mass number A, then you can use A minus Z, you can find out the number of neutrons. So we don't need to write down the number of neutrons. Okay. So you can think about, you can argue, why do we use X and A? How about X and N? Of course, that's also okay. You can, instead of saying hydrogen 1, okay, indicating the total mass number is 1, the no neutron, you can also write down X, N, right? So hydrogen 0 here, okay, so no number of neutrons. So that is also okay. So, but we don't, in reality, we don't really use this because the subscript is often preserved for something else. It indicates the number of items. So like, for example, we use for water, H2O, right? We get H sub 2O. That 2 means we have 2 hydrogens. But if we adopt this notation in the bracket, then we have to write H sub 0, maybe bracket 2. Oh, so it's more complicated. And it's also confusing. So we usually reserve this subscript N, the location of the subscript to be indicate the number of items and the number of nucleus. Oftentimes what you see is just use this XA to denote certain nuclide. Okay, so that's very basic terminology. And now something slightly more interesting. Then for different nuclei, and they can have the same number of protons, but different number of neutrons. Okay, it's like the examples I mentioned before, like hydrogen. We can have hydrogen, deuterium, tritium. Okay, so in general, for a series of nuclei, if they have the same Z, okay, but different N, the same number of protons, the same chemical element, but different number of neutrons. So their chemical properties are the same because they have same number of protons, so they have same number of electrons. But they have different number of neutrons. The number of neutrons do not affect their chemical properties much because neutrons do not have charge. Okay, so they don't really affect the behavior of electrons much. I won't add much here because indeed they are going to affect the behavior of electrons a little bit, not completely irrelevant, but the effect is oftentimes very, very small. Then we forget about the effect of neutrons on the chemical properties of the element. Okay. So for a series of elements, you have the same number of protons, different N. If they have a different N, then they're going to have a different A. And we call them the isotope. Right. So for example, we have a hydrogen 1, hydrogen 2, which is deuterium, and we have hydrogen 3, which is a tritium. Okay. Then when we see this symbol, of course, this 1, 2, 3 indicated the mass number. So when I add the number of neutrons and protons together, how many nucleons do we have? And if you want to know the individual number of protons and neutrons, we have to look up the periodic table by knowing the chemical symbol H. We look up the dictionary, the periodic table, and I tell, oh, so hydrogen will have 1 proton. Okay, so then we can put in the numbers, we can fill in these numbers on the left-hand side. So this will be 1, but we don't write it. Okay, then we have this 1, and we can subtract the A and Z, we get N. So here in this case, hydrogen has 0 protons, 0 neutrons, 1 neutron, and 2 neutrons. Okay. So as long as we write down this black part, the chemical symbol and A, then we can find out the other 2 numbers. We don't need to write them down. Okay. So for this series of elements, they have the same Z. So that's why all of them are hydrogen, they have the same chemical properties, but they have different number of neutrons. Then we call them the isotope. Okay. So isotope is probably among the following 4 terminologies. Among the following terminologies, the one you're most familiar with. And the second terminology will be, so if the nucleus have the same A, the same number of mass, okay, but different Z, okay, different number of protons, and of course they have different number of neutrons. So in this case, we call them isobar. So for example, let's take a hydrogen 3 as a tritium as example. We take tritium as example. So same A, we can have another nuclide with the same total mass, okay, 3. But let's say if we change one neutron to 1 proton, then we're going to have 2 protons and 1 neutron. Okay, so that is helium. So tritium and helium-3 are called the isobars. Okay, so this terminology is important is in certain nuclear reactions, when very important nuclear reactions, we convert neutrons, we convert between neutrons and protons, either from neutron to proton or proton to neutron. In those nuclear reactions, the total mass number doesn't change, but number of neutrons and protons can change. So this example is the beta decay. So that includes both of the beta plus decay and both beta minus decay. Okay. So in this beta decay process, we either release an electron or we release a positron. Okay. And the mass of electron positrons are the same. They are so small compared to the mass of neutron protons. So the total mass number doesn't change. Okay. But the number of protons and the number of neutrons can be different, just like in this case. So we call them the isobar. Okay. So next one, how about if the nucleus have the same number of neutrons, same number of neutrons, but different number of protons, and thus different number of mass. So in this case, we call them isotone. Okay, this is less commonly used compared to the other two, but if you need it, the name is there. So one example would be, let's say, the same number of neutrons. Let's take helium-3 again as an example. So helium-3 has two neutrons, two protons, one neutron. So helium-3, we have one neutron. So let's keep the number of neutrons to be the same, but let's reduce the proton. So instead of two protons, one neutrons, we have one proton and one neutron. And that is exactly the deuteron. Okay. So deuteron and helium-3 have the same number of neutrons, one neutron, but different number of Z. So deuteron has one proton, and helium has two protons. Okay. So that's why they're called isotone. Okay. And so this is used less common than the other two. Of course, isotope is the most commonly used. And the last one, it's interesting, and that's really related to quantum mechanics. For two nuclei, they can have the same number of all of them, Z and A. Okay, but think about let's say deuteron as an example, neutron-proton interaction. Okay. And if we want to measure the energy of this system in quantum mechanics, we need to know the interaction potential. So in nuclear case, we can approximate the interaction potential as a square wave potential. As soon as we do that, then we know the energy of the system is quantized. Okay. So the state of the system is discrete. There can be multiple discrete states corresponding to different energy. Okay. And the first state, with the lowest energy, it's called the ground state. It's called the ground state. It has the lowest energy close to the ground. And the other states, we call them excited states. So let me quickly draw like the energy levels here. We can have multiple energy level or multiple states. Okay, and the distance of distance between them means the difference in energy between them can also be very different. Let's see, this is psi 1, psi 2, psi 3, all of them. Okay. And first one, this first state, we call it ground state. And all the rest of them, we call them excited state, because they have high energies than the ground state, so they are excited. So for nuclei, different nuclei, if they have the same number Z and A, they can still be at a different quantum states. Specifically, they can be at different states. So in this case, we call them isomer. Okay. So give me one example. You can say like PA. So PA 234. PA34. You can look up the periodic table and find out the atomic number is 91. So for this element, we have PA 234, but 234 only indicates the total number of nucleons. So this element or this nuclide can have more than one excited state. Of course, for other elements, a lot of excited states are not stable, so their lifetime is short. They quickly go to the ground state. But for PA234, it actually has a quite a stable excited state. And for that state, we call it 234M. So add M here to indicate that although it's the same nuclide, but at different quantum state, okay, we call them isomers. Okay, so these are the four terminologies. Of course, among the four of them, the most common one is the isotope. And for isomer, I want to warn you, this word has been used in chemistry as well. So it should be distinguished from the chemical isomer. Okay, this is the nuclear isomer. And as you may notice, all these terminologies are close related to one very important table or chart we use in nuclear engineering or nuclear physics. It's called the chart of nuclei or the table of nuclei. Table or chart of nuclei. Okay, so what is that? So that is a chart when we put on this Z versus N table. Okay, either Z versus N or N versus Z. And for every element Z, we just draw somewhere between. For element Z, then we can have multiple isotopes. We can have multiple isotopes. Then we can put it here. Like every dot represents one isotope. So because they have the same number of Z, different N. So those are the isotopes. Now if you look at vertically, so the same number of isotope. Okay. So this will be isotope. Let me write it down. If you look at the vertical line, so different number of N. So we can have elements with the same number of N, and we call this as the vertical cut will be the isotope. Okay. So overall, if you open the chart of nuclei, so every pixel on this chart represents one nuclide, and most of them will be on this curve. Draw it here. So if this is a Z, equal to N. I'll draw a diagonal line. So this is Z equal to N. And most of the nuclei are close to the Z equal to N. But as we look at the heavier and heavier nuclei, and this the distribution is going to bend down a little bit because many elements, many nuclei have slightly more neutrons than the protons. Okay, so most of the stable nuclei fall onto this slightly bended curve, and it's larger than Z. So one important task after learning this chapter is understand this table or this chart of nuclei. So as a nuclear engineering, then we need to understand chart of nuclei. Just as a chemist needs to understand the periodic table. The periodic table tells us essentially the chemical properties of every element. And the chemical properties have nothing to do with the number of neutrons. But for nuclear physics or nuclear engineering, then the nuclear properties actually depend on the number of neutrons by a lot. So every group of isotopes, they have very different nuclear properties. So in that sense, our periodic table has to expand along the third dimension. The third dimension is the number of neutrons. So our periodic table, this is our periodic table. It's much bigger than the chemical periodic table. And it's not easy to align them in 3D because we have the third dimension of 3D table. That's why I put it just on this table, chart of nucleus. And you can see multiple elements on this chart of nuclei. I hope I can draw that. Maybe I can use this to draw it. So something like this. So it's centered around there's a stable nuclei line, and along Abraham's horizontal cut, we have multiple isotopes. Okay, and if you click every pixel on this chart nucleus, then you can find out this terminology we just mentioned, XA. Okay. And you can find out, what is the chemical symbol, and then what is the associated numbers like A, N, and Z. And in addition to that, sometimes, like in this case of isomer, you can see next to the total mass number, we have this letter M. And the meaning of that is this nuclei is in a different excited state. Okay. So in a nutshell, the goal of this chapter on this nuclear physics is for you to understand this table or chart nuclei. So in the future, given a chart nuclei, if you click every pixel, you should be able to understand what the different numbers mean. Okay. And many of the properties are easy to understand, like this number of neutrons, number of protons, they're easy to understand. Some of them are slightly more difficult to understand, like those excited states, because we need to know at least some basic quantum mechanics. So, and there are other quantities we haven't talked about yet. For example, one important one is the spin. It's a nuclear spin. Okay. And usually we use the capital I to represent the nuclear spin. So the nuclear spin sometimes integer, like 1. Sometimes it's a half integer, like 1/2, 3/2, half integers. So to understand nuclear spin, so briefly, you can treat out the spin as what do the spin mean? Spin means angular momentum. So nuclear spin represents angular momentum. It's angular momentum. But in quantum mechanics, angular momentum is not the same as a classical angular momentum. So angular momentum itself is quantized. You cannot take any arbitrary value. And even worse, so angular momentum in the classical physics is a vector. Right? So in the classical physics, it's a vector. So it's a vector. That means we can know the 3 components, x, y, and component at the same time. But in quantum mechanics, this is not the case anymore. It's not a vector anymore. And we are going to cover that in the next semester. So in quantum mechanics, so these three components are three quantities. You can call it Lx, Ly, and Lz. It's not guaranteed that we can have three quantities at the same time. So whether we can know two quantities at the same time is bounded by the uncertainty principle. So we need to compute the commutator between these two operators. If the commutator is 0, then fine, we can get to know the values at the same time. But if the two do not commute, meaning the commutator between two are not 0, then we cannot know the two of them at the same time. It happened to be the case of this angular momentum. We have three components, this x, y, z component. But unfortunately, they don't commute. So we cannot even draw a vector because we don't know the three components at the same time. If we know two of them, then the third one is completely spread out. Okay. So going back, roughly nuclear spin is an angular momentum. But this angular momentum is very different from classical angular momentum. And we need to introduce actually a lot more new maths to describe this spin. Okay, so but if you click the chart for nuclei, for every nuclei, you can see this spin. This is one number, I, could be 0, could be 0, could be 1/2, etc. So because some of the quantities, you have to understand some of the quantities, you have to wait a little bit longer to introduce more quantum mechanics. But a lot of them can be explained in this class. For instance, the shape of this curve. Why do we have a slightly banded curve on this chart for nuclei? And that's related to the binding energy. Like that is an important topic we're going to cover in the next few lectures. Okay. So that's that. We have 5 minutes left. In the last 5 minutes, let me just give you a few important examples, of isotopes. Okay, and we mentioned already mentioned one of them. So it's hydrogen. So hydrogen 1, hydrogen 2, and since we use it so much, just use one symbol D, deuteron, referring to the nucleus, or deuterium, referring to the atom, or H3, tritium. Okay, so those are hydrogen isotopes. And being a student of Illinois, we should also know helium-3 and helium-4. Oops. Okay, and the reason is that these two are related to the so-called superfluid. Okay, the physicists of Illinois made a lot of contributions in the superfluid, and helium-3 and helium-4 can form the superfluid phase. So the first one was discovered by discovered on helium-4. So helium-4 being actually a sort-called boson related to the spin state. And when we put out bosons together, it's interesting for bosons that you can put all of them to the ground state and form this state called BEC, Bose-Einstein condensation. And that is the reason we have a superfluid helium. So the helium-4 below certain critical temperature can flow without any resistance. And the physicist, like our physics department, Anthony Leggett, so won Nobel Prize because of his work on superfluid. Okay, so he's still in our physics department. In fact, without the pandemic, you can actually see him quite often on campus. I've seen him a couple of times at the cafe in the library. Okay. So let me see what else. Carbon, right? Carbon 12 and carbon 14. So carbon 14 has a lifetime, half-life of roughly 5,700 years. And this half-life is very close to the lifetime we want to use to characterize our world, right? A few thousands of years. And that is exactly used for technology called carbon dating. So by looking into how many carbon-14s and materials, then we can tell how old they are. Okay. So and the last two examples will be uranium. So two uranium isotopes, to uranium-238 and uranium-235. So there are a bunch of isotopes we use, and these are some of the examples. Okay, I think that should be all for today. So next time we'll cover a little bit more of on some of details into some of these quantities, like the mass of the nucleus. So although we add up the mass to be the sum of the number of neutron protons, if we look inside the nucleus, the distribution of the mass is not uniform, actually close to uniform, but not entirely uniform. And that is important for us to understand the binding energy and ultimately the charge of nucleus. Okay, so that be the topic for the next time. Okay, I'm gonna stop. Okay, it seems my iPad was frozen. I think let me stop recording.